part 2, which is 2 reactions, so we'll talk about that today. You have a quiz. Anything from experiment 7 is fair game on this quiz now, so be prepared for that. Your experiment 3 conclusion rewrite is due this week. Some cleanup notes here. First of all, make sure you clean your glassware well and your hood before leaving each week. Also, a lot of thermometers have been left on, so turn those off. And there's been a lot of garbage in the glass waste, so please keep garbage out of glass waste. Glass waste is for glass. Global Missions Conference. Last call here for anyone who's attending Global Missions Conference and in a Thursday lab. You need to see me after lab lecture today. Next week, we're going to be doing experiment 8. I'm going to talk to you here in a second about the glassware you're going to need. You need to read this experiment very carefully. It is very important that you follow the directions every week in lab, but it's very important for experiment 8. You can quickly go south on you if you don't follow the directions. So make sure you read it carefully. Make sure you're well prepared next week. The other thing is we have glassware that we're going to have to get in the oven, which I'm going to give you that list here in a little bit. So you will need to be attending lab earlier than normal next week. So morning labs prepare on 7:15. PM labs 12:45 because we got to get glassware in the oven, so it's in the oven by the time lab starts. It's a lab that takes all 5 hours, so be prepared for that. We haven't had one of those in a little bit. Okay, and you need to know what you're doing and be able to do it quickly and efficiently the way it's written. You are going to get your specific reaction for experiment 8, so you all don't have the same reaction. Not everybody's doing the same thing, okay? You will get your specific reaction from your lab prof this week. You need to write the pre-lab for experiment 8 based on that reaction that you get from your lab prof. That's why we're giving it to you this week. Next week, also, experiment 6 report is due, and then in 2 weeks, your experiment 7 report is due. So we are in that fast-paced move on to the end of the semester where things are happening quickly. Okay, so experiment 8 glassware. What you are going to need, first of all, your 3-net brown bottom flask. And some drawers have a 250, some drawers have a 500. It doesn't matter the size. You want all this glassware clean and dry this week. You will not be able to clean or dry anything beyond in the oven next week. So it has to be prepared before you leave lab this week. In that flask, you want to put your 1-inch stir bar. Next thing you want is your Liebig condenser. So that's your wider condenser. You need to make sure there is no water in the jacket of it as well. And so we can show you in lab this week how to take care of that. But you can't have any water in the jacket because then that'll make the whole oven wet and it'll prevent everybody's glassware from getting dry next week. You need your separatory funnel. But you don't want your Teflon pieces in the oven because they will melt, okay? So just keep that in mind for next week. Or you may want to take them out and put them together separately this week so they don't go in the oven. And then you're going to need your 2 glass stoppers. And so we are having you guys come early because we need the ovens packed by the time we start lab next week at 7:30 or 1 o'clock. Because then this glassware has to get to temperature and then stay in the oven for a half an hour before you can do anything forward for the reaction, okay? So keep this list in mind, and this week, especially when you've got your reflux for your second reaction, that would be a good time to be getting all this glassware together, okay? All right. Now let's look at experiment 7. We're going to take your bromoethylbenzene from last week, no matter what condition, and it may look different than it looked when you put it in in your drawer last week, okay? We'll take your bromomethylbenzene, and you're going to react it in quinoline. So we'll talk about here in a minute why quinoline. And then you will get styrene out, okay? So the mechanism for this reaction, it is this. It's an elimination reaction, which you guys are in like a couple weeks about to talk about. First, you'll probably talk about substitution reaction mechanisms, and then you'll talk about elimination reaction mechanisms, okay? So this is an example of elimination reaction mechanism, and your quinoline is your base. So your quinoline is deprotonating your bromomethylbenzene, and by it deprotonating your bromomethylbenzene, that's helping then cause the loss of your bromine. So in the end, you go on to lose, or the quinoline becomes protonated, is a charged positive species. We lose our bromine. The counterion for the quinoline is then the Br minus. This all happens in one step, so that's important for figuring out what type of mechanism it is. And it's really important that we use quinoline in this reaction and not something else. So we're going to talk about that, all of that, right now. So like I said, this is an elimination mechanism. And it's known as E2. So in a couple weeks you'll hear more about E2 and know what that means. This all happens in one step. So E2 mechanisms occur in one step, where we break the CH bond and we break the C halogen bond and then form an alkene from it, okay? It's also known as a beta elimination, or you could call it a 1-2 elimination. Now, the reason that we use quinoline is we need what is called a non-nucleophilic base, okay? So we need a base that once it goes and does its job as a base, we don't have a nucleophile left around to react with what is there, okay? Or even before it does its job as a base, go on and act as a nucleophile instead of a base, okay? So in this case, we couldn't use, we can't use KOH, we can't use NaOH. These are nucleophilic bases. These would lead to most likely more substitution than the elimination reaction, or at least compete with the elimination reaction, okay? And so we can't use our nucleophilic base. Another example of a nucleophilic base is pyridine. So quinoline and pyridine are very closely related to each other. That's pyridine. We can't use pyridine because the boiling point is too low. So pyridine's boiling point is about 115 degrees. That is too low because as we're making that styrene, we're collecting this between 120 and 160 degrees. So we need a base and a solvent. This is also the solvent for the reaction that's not going to boil away before we actually collect the product that we want to collect, okay? So quinoline's boiling point is about 237 degrees. So it's high enough that it's not going to leave with the styrene, okay? Now, with this reaction, we use heat to drive the reaction, and again, we're collecting our styrene between 120 and 160 degrees. Before we get to that 120 degrees, we're probably going to have a lower boiling fraction. What should most likely be in that lower boiling fraction from last week? That you were trying to distill off last week? Hexane, right? So probably, in the 60s, 65, 70 degrees or so, you should be collecting hexane. You're going to collect this separately than you do your styrene, okay? So you want to keep that as a separate fraction. But it's important that you get the volume of this hexane. That is why you took the volume of your product last week, okay? So that you could subtract this volume from your product volume to then recalculate how much is actually bromoethylbenzene versus bromoethylbenzene with a little hexane left over, okay? So don't forget to collect that volume measurement and then use it to recalculate your yield from last week, okay? Then we'll have our collection of our styrene, and there may be impurities in between here, okay? So you don't want to start collecting your styrene till 120 degrees, and you don't want to keep collecting beyond 160 degrees, okay? And you're going to collect it in your sidearm test tube, so it'll be a lot like experiment 6 when you were distilling your unknown. You collected the impurities first, and then you collected your product as it was boiling over, okay? Then anything above 160 is probably starting material. And then also, we're forming our quinolinium salts in this reaction, so that's going to be in there too, okay? We're not going to collect anything above 160 degrees. So at 160 degrees, you're going to stop the distillation, okay? Then what you're going to have to do is this quinolinium mixture, whatever is left in that distillation, so you're using your all-in-one simple distillation apparatus. Everything that's left in there likes to form this hard glass-like substance in the glassware that you can't get out if you wait until it cools down completely to clean it. So you're not going to wait till it cools down completely to clean it. What you want to do is, in your hood, while this distillation is occurring, you want to have some toluene in a beaker, okay? Then you're going to let this cool slightly to where you can handle it with your hot pad, okay? So not bare hands, but handle it with your hot pad. And you're going to pour the rest of that reaction mixture into your organic waste. And you want to make sure you have gloves on too, so that in case a little bit is splattering because it's hot, okay? So be really careful, carefully pour it with your hot pad, make sure you have gloves on to protect your hands. Then you're going to take some of that toluene and add it to the distillation apparatus and rinse the distillation apparatus with toluene a couple times to get the rest of that mixture out of there, okay? If you wait to clean your apparatus, you will not get it clean, all right? So you need to, as soon as you're done with the distillation, you need to make sure that you are ready to clean up, get your styrene in a safe place, and then be ready to clean up that apparatus. One thing that adds to the glass and glass-like mixture that forms, the salts, and there's some polymers that form, is the longer you heat it. So you don't want to slowly get to 120 and slowly distill off your styrene. You want to heat up your reaction, don't give it full heat, but you want to go quicker versus more slowly to get up to collecting your styrene so that there's less time for that whole mixture to sit there and just cook and make more muck in it, okay? All right. Questions with that part? Now your styrene, you're going to, you need to get the yield of your styrene, okay? So figure out how much yield you have, and then you're going to see your instructor, okay? And when you get the yield of your styrene, probably the easiest way to do that is in the round bottom flask that you're going to do the next reaction, okay? So get the tare weight of your round bottom flask, add your styrene, and then in that round bottom flask, have your styrene, come see your instructor, and we're going to supplement the styrene, but you need to know how much you are getting, okay? So you need to know your styrene, and you need to know how much you got from your instructor, all right? So make sure you enter both values into your notebook, because that is going to contribute to your yield of the polystyrene, okay? And no matter what yield you get of styrene, we will give you some more styrene, okay? So even if you've got like the greatest yield of everyone in the classes all together, you are still going to get styrene from us. It just helps with the polymerization reaction a little bit better for you to get better results at the end, okay? So then, after you have the styrene that you need, you're going to be setting up the radical polymerization, okay? And so, one of the pieces that you need for that you're going to have styrene, and then you are using AIBN as a radical initiator this week. And this reaction is going to be done in refluxing toluene. So that AIBN is what starts that chain reaction. So with heat, our AIBN reacts and becomes, we get 2 radicals out of 1 molecule of AIBN, and then we get some nitrogen gas that comes off. So you may see some frothing in your round bottom flask. It shouldn't be as vigorous as it was with the benzoyl peroxide. It should be more kind of frothing versus a real big exotherm that occurs when you start heating, okay? But you'll heat again with your heating mantle. And what happens is that AIBN is basically the start of the formation of each chain of polystyrene, okay? So an AIBN radical will react with 1 molecule of styrene, and it then forms a benzylic radical, okay? So the radical is on the benzylic carbon, not on the carbon next to the benzylic carbon. Then that radical goes on and reacts with more styrene, and so on and so forth, okay? So what you want to be careful of is with that AIBN, you only use 30 milligrams, okay? Or 0.03 grams. If you use more than that, you're not going to make very long chains of polystyrene. You're going to make many chains of polystyrene, but you're not going to make very long chains of polystyrene, okay? And so the thing with the polystyrene is if you have a lot of AIBN, your N is going to be really small. You'll have really, really small chains. And what's important here is the polystyrene is soluble in toluene. After you are done with this reaction, you're going to cool everything down to room temperature. And then you're going to add the reaction mixture to rapidly stirring methanol. Okay? And what happens with the methanol is the methanol will precipitate large chains of polystyrene, but the small chains and any starting material are going to be soluble in the methanol. Okay? So if you use too much AIBN, you're not going to get a lot of precipitate out. You're not going to recover a lot of polystyrene. All right? So you want to be careful with how much AIBN you use. And just like with benzoyl peroxide, it's a radical initiator. There's the potential that it's something that could be explosive, so you don't want to grind it between glassware joints, things like that. We keep it in the freezer until it's time for you to use. Okay. So when you're adding this reaction mixture to the rapidly stirring methanol, what you want to get are like flakes of polystyrene. If you get globs, and that doesn't sound very technical, but that's really just what it looks like. It looks like kind of slime globs. You've trapped toluene in the polystyrene. And so it's going to be kind of hard to isolate, and it's going to be hard to work with. So what you don't want are globs. What you want are flakes. So when you're adding the mixture to your methanol, you want to do as this figure in your lab manual shows you. You don't want to just chuck it all into the rapidly stirring methanol, okay? You want to just carefully, slowly add it to the methanol so it has time to precipitate out the polystyrene and not get the toluene stuck in the strands and in the flakes and so forth that you're trying to precipitate out, okay? So be really careful with this precipitation. After you've added it, you're going to stir for a specific amount of time, and then you're going to do vacuum filtration to isolate your polystyrene. Sometimes that vacuum filtration can be a little bit tricky because, again, you've got short chain polymer and long chain polymer in it, so the short chain polymer wants to clog up filter paper and slow things down. Or it may want to just filter all the way through your Buchner funnel. So what you may have to do if things aren't working well with the filtration is you may have to use more than one piece of filter paper when you're doing the filtration, okay? Then when you are done this week, you're going to dry the polystyrene. Okay, so it needs to dry, air dry. You need to collect an IR spectrum. And you also need to collect a yield. You can check, if you're done in time this week, you can check and see what the IR spectrum looks like. If it has a big OH peak in it, so polystyrene shouldn't have a big OH peak in it. If it has a big OH peak in it, then you probably still have methanol on it and it needs to dry longer. If you don't, then you've lucked out and the IR you've collected is fine to use. You're collecting the IR spectrum of a solid, so on the ATR you're going to, like you did with experiment 6, you're going to collect the background with the anvil up. But then with the solid, you're going to put the solid right where you did the liquid of your unknown, but put the anvil down when you're collecting the IR spectrum. Okay, so that's the only difference from what you did with experiment 6 is the solid, the actual experimental sample you collect with the anvil down. Okay. Around the labs, there's standard IRs for polystyrene posted. I'll also post one on Moodle so that you know what it should look like. You talk with your lab prof, but most likely you don't need to print that because everybody will have the same standard IR spectrum that they are comparing to, so we could save some trees by everyone not printing out the same IR spectrum when you go to do the report. But that is the spectrum that's your literature spectrum. So what I put on Moodle is going to be the literature spectrum that you compare to, similarly to your literature spectrum that you had with experiment 6. It's just you're not going to pull it out of the literature. Okay. So when you write your report, just make sure you remember to look for that on Moodle for comparison. Okay. The other thing we're going to talk about here is GPC, and I'll tell you what you're going to do about that for your sample. Okay. Okay, so for experiment 7, we're also going to use a technique called gel permeation chromatography. This is also known as GPC, or it's also called size exclusion chromatography. Okay. And this is an analytical technique that's usually used to look at really large molecules, so especially polymers. And the way that it works is you're going to run a sample through a column, and in that column is polymer that is attached to it, but it's not just one nice coating of polymer. The polymer kind of makes kind of like English muffin nooks and crannies in the column, okay? And so then the sample runs through all the nooks and crannies and then comes out the other side, all right? Now smaller molecules sample all of the nooks and crannies. So what that means is they go through and go through all the different paths that the sample can go through, okay? That causes the sample to elute. When we're talking about chromatography, that's what we talk about, how we talk about the sample leaving whatever type of chromatography we're going to do. The sample always elutes or comes off, in this case the column, later. So it's kind of inverse of what you would think, smaller molecule eluting later versus earlier. And that's because it's spending so much time going through the column, okay? Larger molecules elute earlier, okay? And that's because they just can't fit in all of the different channels as they go through the columns, so they actually go through the columns sooner, okay? So when you're looking at data from anything chromatographic, the data is called the chromatogram. Okay. And so if we got something like this, the larger molecules are going to elute earlier. So this is probably going to be polymer earlier versus these nice peaks are probably going to be monomer or dimer or trimer, okay? Much smaller than the polymer compound, okay? And so that's what you would see in the chromatogram. Now, in this semester, we're going to look at a number of different chromatographic techniques. With chromatography, there's always two phases. There's a stationary phase, and there's a mobile phase. So our stationary phase is this cross-linked polymer coated column, okay? So the stationary phase is just like it sounds, it doesn't move with whatever species is running through it, okay? Versus the mobile phase in this case is the solvent that is running through the column, okay? So that's kind of basics of gel permeation chromatography. So there's different values that can be calculated from this. So I'm going to go through what all those are and go through the different calculations. So for the gel permeation chromatography, you are getting molecular weights out of the analysis, okay? But it's usually not going to be, especially when you're looking at a polymer, it's usually not one number that you're going to get out of it. So in our experiment, we're not doing anything to control the size of the polymer other than telling you don't use too much AIBN so you don't get too much small chain polymer. But we're not making it, you know, our N on our polymer isn't exactly 500 chain lengths or something like that, okay? And so there's two different averages that can be calculated. There's the number average, or the simple mean, and this is signified by M subscript N, okay? And this is a number average molecular weight. So all of the polymer strands, no matter what size they are counted equally. All right. Then there's also the weighted average. And this is denoted as MW, so M subscript W. In this case, your bigger polymer strands are counted more than the smaller strands. So I'm going to go through some examples so you can see the difference between the two calculations. So we're going to use the example that is in your lab manual. If we're looking at football players, and we're looking at the number of players at a specific weight. So we've got one that's 150, two that are 180, one that's 210, and one and two that are 250. Okay? So if you total just the weight of all these, we're going to need this number, which is 1,220 pounds. Okay? So we'll need it for both of these calculations, just that total. So for MN, we basically just take all those weights, add them up, divide by 6, and we'll get an average. So if you take 150 plus 180 plus 180 plus 210 plus 250 plus 250. Divide it by 6. So we've got our total of 1220 divided by 6. We give an average weight of 203. Okay? So another way to look at that is also if we just said 1/6 times 150 plus 1/6 times 180 plus 1/6 times 180 plus 1/6 times 210 plus 1/6 times 250 plus 1/6 times 250, we get 203, all right? With MW, we're going to take that individual weight into account for each representation of the weight that gets added up to the total, okay? And so with MW, the calculation becomes, we'll take our 150 divided by 1220, and then multiply that times 150. And then we add to that 180 divided by 1220 times 180. So we do that twice. And then we've got 210 divided by 1220 times 210 plus then our 250 divided by 1220 times 250 twice. And when you go through all the math, you get an average of 210. Okay, so it's slightly bigger than our 203 because it counted, in doing the math this way, it counted these larger numbers more than it counted the smaller numbers. Okay? And so whenever you have a calculation of MW and MN, they're at least going to be the same, and if anything, the MW will be greater than MN. You won't have MW smaller than MN, okay? And so there's another number that relates the two, and that's called the Polydispersity Index. So that takes MW divided by MN PDI. And this number is at least always equal to 1, if not greater than 1. Okay? If it is equal to 1, it's considered monodisperse. So what that means is you have done something to control the chain length. You have only one chain length of polymer in that sample, if your PDI is 1. If your PDI is greater than 1, then it's polydisperse. And for samples that come from experiment 7, they can range, PDI can range somewhere between usually 2 and 30. It's kind of all over the map, okay? So for this week's experiment, you are going to make sure, actually let's go back even to the styrene. For the styrene, make sure you have the yield of your styrene, and then you need to know how much you were given to go into the polymerization reaction, okay? So from this yield, you can calculate a theoretical yield, or for this yield, you can calculate a theoretical yield, the yield you actually collect, and then you can calculate a regular percent yield. As far as confirmation that you made styrene, the only confirmation you're going to have, because we need to take your styrene on quickly to the polymerization reaction, is the boiling point range that you collect that styrene over. Okay, so like last week with your bromoethylbenzene, you had the silver nitrate test, you had the density test relative to water as your confirmation of at least making something heavier than ethylbenzene and something potentially halogenated, okay? This week, your confirmation of your styrene is going to be your boiling point. For the polystyrene, you recall from last week, as far as your yield, you're going to take your grams of polystyrene you make, so you'll need to record that yield, over the grams of styrene that you put in, okay? And then you'll get basically a weight percent, okay? Do you know why you do the calculation this way? Versus just doing a regular way? What do you need to know of the polystyrene in order to go on and calculate how much you should make for a theoretical yield? Molecular weight. And your polymer is all over the place, right? So you don't have a, your polystyrene has this specific molecular weight, okay? So that's why you have to do this weight percent yield. There's not a specific molecular weight of your polystyrene that you can use for this calculation, okay? So you need to take the masses and calculate your weight percent. You will also collect, like I said, the IR spectrum, and you're going to collect and compare it to the standard that I give you. And then for GPC, we kind of have a sad story here. So our GPC instrument is not working, okay? So we're not going to use your samples for GPC, but don't worry, we have data for you to analyze. Okay? So I would hate for you to get out of this without being able to analyze data, okay? So you're going to get Data from your lab prof next week. And with that data, you want to analyze the MN, the MW, and the PDI. Now, MN and MW, what are those numbers again?
Average weight.
Molecular weights, right? Okay. So something else you should use this information for is figuring out what the repeat units are for that sample that you're analyzing the GPC data for, okay? Because you can calculate that because you have molecular weights, right? So you'll need to analyze that data. And typically when you are analyzing data for repeat units, you use more often the MW versus the MN, okay? All right? So this is the data that you will need to collect for what you make this week.